Prototype for thermal conductivity measurement of materials made in forest agro-residue. This project is presented by Lilia Ortiz-Rodríguez, Alejandro Sánchez-Pachuca, and Carlos.Cuevas-Suarez from Instituto Tecnológico Superior de Perote in Perote, Veracruz, Mexico. Heat transfer is transmitted in three ways. 1. Conduction. 2. Convection. 3. Radiation. Conduction is a process where one system transfers heat to another system of lower temperature, and both systems must be in direct contact with each other. Determining the thermal conductivity of a material is fundamental in many areas of science and technology, as well as in industry. The Fourier's law regulates this type of transfer, and it is described as the heat flowing in a wall is the product of the thermal conductivity of the material by the difference in the temperatures of surfaces 1 and 2 over the thickness of the material per unit area. Thermal conductivity K is a variable that expresses the capacity of a material to transfer heat. It is expressed as watts per meter per degree Kelvin. This paper examines the hot plate method from the principle of operation, design, and construction of the prototype machine that determines the thermal conductivity of materials that suggest being insulators made from agroforestry waste and PET using the hot plate method. The construction of the prototype is based on the protected hot plate method, following the specification of ASTM C17713. The standard addresses all aspects to be considered when manufacturing a thermal conductivity measuring machine: the characteristics of the material in the plates, the types of sensors, the dimension of the equipment, and the construction recommendations such as determination of the materials to be used. The selection of materials for the construction of the prototype is of vital importance. For that reason, it was based on the ASTM C177 standard to have an optimal performance of the equipment. The equipment plates are made of aluminum. Design of the prototype in the SolidWorks program. The design for its construction was carried out in the SolidWorks program. Equipment materials. After having completed the design, the materials were acquired. Construction of the metallic structure. The equipment was built based on the computerized design, and the entire metal structure was built. Installation of electronic elements. The installation of electronic components, temperature regulators, K-type thermocouples, electrical resistors, Peltier cells, cooling systems, among others, was carried out. Installation and elaboration of the temperature registration program. Having a temperature control is of vital importance within the equipment. For this reason, the programming that controls the K-type thermocouples was carried out according to the ASTM C177 standard. Consequently, the temperatures of the plates are recorded. The measurements of the thermocouples are reflected on some OLED screens through the Arduino boards installed in the prototype. The following table shows the physical specification of the prototype, such as cooling system material, cooling system specifications, among others. The system is made of a Peltier cell. The operation of this system consists of one side of the cell being heated and the other side of the surface being cooled. So the cold side is placed on the aluminum plate and the heat sink is placed on the hot side to avoid overloading the cell, as this figure shows. The cold plate components are of 30 centimeters by 30 centimeter sheet of 16 gauge aluminum, a thickness that does not affect responsiveness was selected due to the time it takes for the material to reach thermal equilibrium. But it should not be so thin that temperature losses occur at the edges of the material. The importance of maintaining a constant temperature throughout the conductivity measurement process is essential. For that reason, the design includes thermal protection on the side of the prototype, insulated with refractory ceramic fiber. This insulator is placed on the four sides of the prototype, including both the base where the lower cold plate sits and the upper cold plate. The authors have shown that the effect of high temperature can increase thermal conductivity through the heat transfer mechanism. The construction of the heating plate was started, which was created from an aluminum plate due to its high thermal conductivity and a pair of electrical resistors. The dimensions of the plate are 30 by 30 centimeters and the electrical resistors are 2 by 10 centimeters with a power of 150 watts. To obtain a broader analysis of the heat transfer in each of the plates, type gauge sensors were placed on the hot plate and the Peltier cell on the plate. Libraries were used for the MAX 6675 modules, for the K-type thermocouples, and for the 32 by 128 OLED screens. The code development has a record of 3 sensors per Arduino. The temperatures are projected on an OLED screen with the sensor number and the temperature that is captured at that moment. To verify the accuracy of the simulation results, the theoretical calculation of thermal conductivity was analyzed using Ohm's law, and the values recorded in the Proteus simulator were obtained. The entire circuit has a power of 150 watts, but due to its series connection, it limits the resistors and generates a power of 31.75 watts. The table shows the result of experimental confirmation of tests on a material with thermal conductivity known as drywall, and the measurements of 3 test specimens of the same material and same thickness with a known conductivity of 0.1005 watts per meter per degree Kelvin. The results are 1.1650 watts per meter per degree Kelvin, 0.1190 watts per meter per degree Kelvin, 0.0950 watts per meter per degree Kelvin, with an equipment efficiency of 61 to 94%, so the results validate the proposed method. The final prototype is presented here. Conclusions. The design and creation of a prototype machine based on the hot plate method to determine the thermal conductivity of materials represents a significant step towards the optimization of thermal efficiency in various products. In this case, the creation of thermal insulators. The design of a machine to determine thermal conductivity will provide university institutions with efficient and low-cost equipment, allowing students to perform practical experiments that complement their theoretical training, giving them a deeper understanding of the concepts and phenomena related to heat transfers. These are the references.